Hello everyone, in this video we will see the efficient way to find the prime numbers in a given range, that is from 0 to n, and where you have to perform various operations and to find continuously find the prime numbers. So let's go into the video and let's start. So first of all, if you are here, then you should know that what is prime number. If you don't know, then I will tell you. A prime number is a number who is not divisible by any other number rather than 1 or the number itself. So that basically means if a prime number is like 2, so 2 is not divisible by any other number like 4, 5, 2, it's not divisible by that. So 2 is only divisible by 2, that is 2 modulus 2 will be 0, or 2 is divisible by 1, that is 2 is only divisible by 1, that is a prime number. So I have written the definition also. A prime number is a number which is only divisible by 1 and the number itself. That means it is only divisible by itself or the number 1, because 1 divides every number. That is the basic thing that you may be knowing. So some examples of the prime numbers are 2, 3, 5, 7, 11, 13, and similarly 17 is a prime number, 19 is a prime number. So that's that. And how to check if whether a number is a prime or not. So I have written the pseudocode. So basically, if you are given a number that is like 11, so you have to check whether it is a prime number or not. So you will have to do one thing, that is you will have to initialize I from 2, that is I from 2, or then you will have to run till the number minus 1. So it will you will have to run the loop till then, and you will check if the given number that is 11 modulus I, I will keep increasing, that is it will start from 2 and 3, 4, 5, 6, similarly it will keep increasing, and you will check if any number gives the modulus of 11 modulus any number that is less than 11 is equal to 0, then the number is not prime. If it is not so, that is 11 cannot be divided by any number rather than the 1 and the number itself, then it is a prime number. So I have written the pseudocode. We will have to initialize I from 2, and it will run till n, because we don't have to initialize I from 1, because 1 will surely divide any number, so it will give the wrong output, that is it will give prime number. It is not a prime number. So we will initialize I from 2 to n minus 1. It will actually run from n minus 1, because number also divides itself. So 11 divides itself, so it will give wrong output. So we will run a loop while I is less than equal to n. Then we will check if at any index n gets a modulus of that index is equal to 0, so we will return false, because it is not a prime number. If eventually if we end this loop and it does not return false, then the number is surely prime numbers, and then we will return 2, and we will keep incrementing I. So it takes time complexity of n, and if your n is large, like something 1000, so you will have to check for many indexes. So to optimize this, a small trick is there, that is we can, instead of checking for running I for less than equal to n, we will run till n under root n, that is we will I multiply by I less than equal to n. So we will run till under root of n. Actually I don't have any symbol to write under root, so we can improve the time complexity to root n, that is till here, from n to root n, if we run the I to I square less than n. So because if number does not have, you may be knowing that if number does not have it is not divisible by any number till n root n by 2, then it won't be divisible by any number after n by 2 to n minus 1. So that's why we can just write it instead of running the loop from I to n minus 1, we will run it till just a second, we will run it till I square less than n. So that's one tweak that you can do, and it will surely optimize your solution, because you are almost slicing the iterations to half. So that's a good thing. But if this is for checking if you want to check only single number is prime or not. If in a question you are given that you have to check for many queries that it is a prime number or not. If you are given you have to check for 100, then you have to check for 3, then you have to check for 56. So similarly you will have to run many loops to check for the prime numbers, if they are prime number or not. So basically in this solution you are just wasting your time, because if you have checked if number is 100 is prime or not, so you can maintain a pre-computation. You can make an array where you can define whether number is prime or not. You can check from there or refer from the index if that number is prime or not. So it will save your time by using extra space. So it is a good optimization, and lot of coding questions require you to do this in competitive programming also. So the method that we are going to study is Sieve of Eratosthenes. You can spare me for the pronunciation because it is really difficult. I have kept the how to pronounce it. I have kept the words here so you can read Eratosthenes. It is a pronunciation, and basically the meaning of the sieve here is to filter. So basically we have to filter the non-prime numbers, or we have to filter the prime numbers out of the non-primes. So that's the thing that we need to do. So as I told you, we have to maintain an array where we will keep the all the numbers from 0 to basically we have to use 0 because instead of using 1 n plus 1 for I plus 1 for the indexes, we will keep 0 and 1 and we will set them to false. So basically we have to maintain we have to make a boolean array from the number to the till the number, that is n. If you are given n is I have taken example 50, then you will maintain an array from 0 to 50, that is n plus 1, basically n plus 1. So that's one thing. And we have to, in this we have the basic idea is, I will show you the idea first of all. We have to iterate, start from the 2. We will make this 0 and 1 false. We have to first of all we have to initialize all the values to true, that is all are prime number. First of all we are getting this assumption. Then we will do one thing, that is we will start iterating from 2 and we will see true is false, true. First of all elements are having value as 2. I have written only the indexes here. I have not written the values that are true and false. These are the indexes. So first of all, imagine that 2 is true. Yes, 2 is true. It is a prime number. We will check if it is a prime number. Then we will again run a loop. It is a prime number. Okay. Then the multiples of 2, that is 4, 6, 8, 10 won't be prime number. You can see that if 2 is a prime number, okay, then the multiples of 2, that are multiples of 2 won't be prime. You can check that if 4 can be divided by 2, yes, and 8 can also be divided by 2. 8 modulus 2 will be 0. Just second, 8 modulus 2 will be 0, and similarly you can check for 48. So then also it can be divided by 2. So it is not a prime number. So on this assumption, when we reach an index which is marked as 2, we will mark it as we will let it as true. It is a prime number, and we will mark all its multiples as false. They won't be prime numbers, because if 2 is a prime number, then its all multiples won't be prime, and if 3 is prime number, and then its all multiples won't be prime, because they can be divided by 3. Like 3 into 3, 9. So 9 can be divided, 9 modulus 3 is 0. So that's why it is not prime. So you can check for 21 modulus 3 will be. So that's how it works. Now we the pseudocode is make a boolean array. So okay, n plus 1 size, we have make the boolean array. Then we will initialize the array with all true values. These all values are first of all true. Then we will mark 0 and 1 index as false, because 0 and 1 they are not prime, so we will mark them as false. Then we will start iterating from 2 till n. Then we will check if the value is true. Basically 2 is true, so yes, it is true. It is true, and we will mark all the multiples of 2 as false, that is 4, 6, and at the end we will be left with a boolean array where only the prime numbers will be marked as true and all the non-primes will be marked as false. So I will use a different color. So I will use a color and then we will check iterating. I will mark the non-prime numbers with this green color. So first of all we will check 2. It is true, so yes, it is a prime number. Then we will mark the multiples of 2 using another for loop as false. So 4 is a multiple of 2, so it cannot be prime number. So understand, I am marking only the numbers which are multiple of 2 as non-prime. So I am marking them as false. I am using this green color to mark them as false. 6 is multiple of 2, so it is not prime. 8 is multiple of 2. Similarly 10, 12, you can check that. 14, 16, and 18, 20. So they are not multiple. They are not prime numbers. They are multiples of 2. 22, 24, and similarly 26, 28, and 30, 32, here 36, 37, 36, and 38, 40, 42, and similarly 44, 46, and 48, and 50. So we have marked them as they are not prime numbers. So we have marked them as false. So similarly, we will iterate to next index, that is 3, and it is also true. So we will it is a prime number. So it has not been marked by the 2 as a non-prime. So 3 is a prime number, so we will mark its multiples as non-prime. So that is 3, 9, and then 15, then you can see 21, so they are not prime. And similarly 27, and you can see 33, and not 37, 39, and similarly okay, so that's how it, and the 45 also is a multiple of 3 because 1 and 5, so that's one thing. And now we will come to 5, and similarly we will check 5 is a prime number, because now you can see it is not marked as false, so it is a prime number, so it is true. So now we will mark the multiples of 5 as non-prime. That will be 7 is not a multiple of 5, 11, 13, 15 is already marked, 16, 17, 20 is already marked, so you can check. And 25 is a multiple of 5, so it won't be a prime number. And 30 is already marked, and 35, okay. Now similarly these all numbers, and 45 is already marked, and these are the numbers we are left with. Now we will go to next index, that is 6. So 6 is marked as false, so it is not a prime number, so we won't have to like go to its multiples then mark them as false. So now we will iterate to continue, just leaving this index. We will jump to 7. Now 7 is a prime number, so it is not marked as false. So now we will mark all the multiples of 7 as non-prime. So multiples of 7 are 7, and then 7, 19, 23, they are marked as 14 is also marked as false, first of all before only. So you can see a lot of our time is getting saved, because we have marked most of the numbers will marked at the first and second index only, that is 2, and in some iterations only most of the numbers will be marked as false. So 49 is a multiple of 7, so it won't be a prime number. So now similarly we will go to 11, and we will mark all the multiples of 11 as a non-prime. 11 is prime. We will mark 13's multiples to like similarly to non-prime, and then we will keep continuing that. And 39 also is a multiple of 3. I forgot that. It will be marked as like non-prime. So 41, 43, they are not, and 47. Okay, so like this we will left with the array of a boolean type whose only the prime numbers will be marked as 2, 1 and 0 and 1 are also not prime, so they will be marked as like green or non-prime beforehand only, before we have marked them as a non-prime at the starting only. So in this array we will keep using this array when we have like, if we are told to find if a number 48 is a prime or not. So we have a array, that is, if you can name it as prime list, okay, the boolean type array. We will check if, just a second, if this index, if the prime of 48 is equal to true, then it is a prime number. So then it is a prime number, else it is not a prime number. It is not a prime number. So this is how we can use the array, and we have pre-computed it, so it won't take any time also. It is a constant space operation, a constant time operation, if we have to check a number is prime or not, if we have this array beforehand only. So you can for many programs you can make this function, and then you can do one thing simply by marking the values as false, and you can check in a program if it requires you to check for many values that it is a prime or not. So this is how we are using this table to just find the prime numbers in the constant time. So here the prime numbers, I will also write the prime numbers so you don't get confused. So the prime numbers from this are like whose values are 2 are 2, 3, 5 and 7 and 11, 13 and 17, 19, 23 and 29, 31, similarly 37 and 41, 43 and 47. So these are all prime numbers that we have found from a range 2 to n or 0 to n. So these are our prime numbers. So this is how we can use as sieve of like this algorithm for finding the prime numbers in a constant time. And for this you have to compromise for the space complexity, because you are maintaining a large array. So if your prime numbers are from like you have to check prime numbers from 10 raised to power 5, so then you will have to make a array of really large size. So that's one like disadvantage of this problem, but it is really helpful if you have to find prime numbers like very much times. Yeah, you have to find prime numbers n times. You have to check a number is a prime or not for a loop, like from 1 to n. You have to check for the indexes if it is a prime or not. So you can use this algorithm for that. So now I will show you the like implementation code in C++ and Python. So here I have written the code in C++. So you can see this is a code from this algorithm. So now I will explain the code. So we have to, first of all, I will initialize the n as 100. So we will find prime numbers from 0 to 100. Then I have initialized a vector of type boolean prime number, and it will be of size n plus 1 because I have to find till 50. So that's why using n plus 1. Otherwise it will make array of 49 size, so that's not what we want. And I have initialized all the values as true, so you can use the vector function. I have I wrote the 2 here only, so it will automatically initialize all the indexes to value true, that is 1. Then we have to manually set the prime list 0 and 1, that is 0th and first element, to false because they are not prime. Then we will call the function. So I have passed the vector by reference. So here is the function, our function that we will use. Now I have passed a vector by reference, so then we can just run a loop, that is from I to 2 because we will start from second value. Then we will use the one optimization that we discussed, I square less than n, that is I will run till root n. So we will check till root n, and we will then we'll check if the prime number, that is prime list I is equal to 2, that it means it is not marked as false, it is a prime number. We will mark all the multiples of that number as prime, non-prime. So this is the loop that we are using. So it will start from square because we have checked for that number, so it will start from its square till less than n. Then j will increment by I, that is if we are marking the multiples of 2 as a non-prime. So you can see, so we are starting from this number, we are on 2, so we will start from 4, that is this index, that is 2 into 2, I into I. Then we will mark all the multiples of starting from here, that is 2, then it will be incremented by value 2, that is 4 5 and 6, then 6 plus 2 8, and 8 plus 2 10. Similarly for the 3 also, it will start from 9, that is 3 square, so 9, and then it will be incremented by 3, that is 9 plus 3 12, 12 plus 3 15, 15 plus 3 similarly 18. So that is how it works. So then it will mark all the false, all the values as false. So as I have passed by reference, so I won't have to return the value vector. So now I will just print them, the values which are true till the last which are true after the calling the function. So we can just print them out and they will be our prime numbers. So let's see. So let's see. So yes, we have got the list of the prime numbers that so these are the numbers which are left till the end as marked as 2, so they are prime numbers. So you can see 2 3 5 7, and similarly till 89 and 97, because the last number prime number before 100 is 97. So that's how it works. So I've written the code in Python also, so you can see here. So I have initialized n to 10 100. Then I have made a list and setting all its values 2 till the n plus 1 index. So then I have manually set the 0th and first index as false, and I have called the function. So in Python, values are passed as reference by default, so I've just passed the list by default as it is. And then we will start from 2, because in Python we don't have on for loop we cannot start from I square. So I will use the while loop, that is p into p less than n. Then we will check if it is true, then we will mark all the multiples of this number as non-prime, so that is false. Then we will increment p by one value. P is for our this, so here we are using for loop, so it will be, so we will start from p square and it will run till n plus 1, and this is where we increment our in Python we have to use the number that we want to increment by. If we have to increment I by 2, so we will write 2 here, so that's what the function of p here. So then we will increment the value, so we won't have to return any value because we have passed by reference in Python by default. So then I will print the values which are true at the last. So I will run the code, so you can see it has run, and we have printed the values. So basically end statement here is to provide the space. If I remove this, so it will just print on the different lines, so that's why I have used this. So you can see all the prime numbers are printed. So if you want to check if we have this list, and if you want to check if a number is prime, so I have got a prime list, and we will check if 99 is a prime number or not. So let's try, and we will print it here if it is a prime or not. So let's see what's happening. Okay, there should be square brackets here. So yes, you can see it is not a prime number, so it is returning false. Similarly, you can check for 19, so it is a prime number, so it is returning true. So this is how it works, and time complexity for this algorithm is Complexity for this algorithm is O of n, then log of log n. So this is the time complexity for this algorithm, that is Sieve of Eratosthenes. And for the time complexity in derivation, as it forms a harmonic series, so you can check the derivation from the Geeks for Geeks site. I will provide you the link. So they have explained it really like in a good way, the how it is derived, the time complexity for this. So here you can see we will form a harmonic series that we will take n common, then we will be left with a harmonic series that is 1 by 2 plus 1 by 3. So similarly you can see the derivation, it is not that much larger, so you can study it yourself. So that's how it works. Then at last we will left with the time complexity of n into log of n. So basically that's how it works. Thank you for watching, guys. Do like this video if you find it useful, and do subscribe this channel and share this video, and do comment down below for more videos like this if you want. Thank you guys for watching. Thank you.